So usual visual cues, keep an eye out for those if you're unsure about what some class rules in case you've forgotten how to be in a classroom. And of course our really quick warm-ups here. So all we're doing, we're remembering our factors of 7, okay? So make sure that we count along with me. So 7, 14, 21, 28, 35, 42, 49, 56, 63, 70, 77 and 84. Counting up in 8s, 8, 16, 24, 32, 40, 48, 56, 64, 72, 80, 88, 96. 9, 18, 27, 36, 45, 54, 63, 72, 81, 90, 99, 100. Righty guys, so what we have here is a really quick warm-up. Only should take you about 5 minutes. It's just on questions relating to content that we looked at over the last couple of weeks. So if you can pause the video, have a go, and we'll check our answers then. See you soon. Welcome back. Let's see how we went. So we had the sum of 3, 3, 3, and 3, 6, 6 equals 699. A little subtraction question, question 2. A multiplication and division. Converting a fraction to a percentage. So at the moment it's just a decimal. So you want to run 4 divided by 8. Would be 0.5. That's a fraction, and you're going to multiply that by 100 to turn it into a percentage, so it should be 50. Expansion question, so we just like to multiply the number outside the brackets by everything inside the brackets. So we're going to end up with 5 times x, just tied it up to 5x, and then 5 times 5, which of course would be 25. Similarly here, so we have 5x times x, 5x times 2, so we end up with 5x squared and 10x. Factorize, so we're looking for the common factor, so I can see that I can write 8x as 4 times 2x, and I could write 12 as 4 times 3. Now what I note is that I have a common factor of 4, so I can take that common factor out the front and leave the remaining 2 terms inside my brackets, and that is what I do for factorising. This one here was a little bit trickier. Remember, we had to FOIL out, so we had first, outer, inner and last numbers all multiplied together, and then we tidy those up. So grouping all of our like terms. The other little shortcut that we found was we had x times x, which was of course x squared, and then we could add 3 and the 4 to get the number in front of the x and multiply them together to get our number at the end here. This one was a little bit trickier. So this is one of our probably extension questions, and what we had to do was, there's a couple of ways, but if you FOIL it out first, so first, outer, inner, last numbers multiplied together, and then we still had to multiply by x right at the end. So if you had some troubles with some of those questions, make sure you fix them up. And on to our new content for today. So we are learning to determine scale factor and ratios between similar figures. Okay, so what you're going to do here, guys, if you can have a look at some of these shapes, and you're going to have a look at them and see, well, which of them are similar. So similar just means that they are the same, well, try again. Same shape, but different size. Give you a sec to have a look. So the sorts of things that we are looking for, guys, okay, so we can see right off the bat that these arrows, they're similar, okay, they're both arrows, but of course they're different size and they've been rotated. We have the semicircles, okay, both semicircles, different size, and they've been rotated, okay, and we all, of course, have, different triangles. These ones here are both isosceles, C and K. I'd probably discuss J and A as both being squares, and of course we could continue that all the way through. So that's basically what we're starting to look at in a little bit more depth, similar shape. So similar figures, guys, as you can see, you have the pen up on the top right hand corner, so we're copying those notes down. Similar figures are figures that have the same shape. They can be the exact same size, or one can be bigger than the other. So we have some examples here. So these similar figures here, okay, the first two ticks, they are similar, okay? They have the same shape, they're both ticks, and they are the same size, okay? So these two, however, the diamond and the house, they are different sizes, okay? But they are still similar because they have all the same lines, right? This is still a diamond and this is still a diamond. So you could imagine that it's been enlarged or shrunk down, okay? The house has been shrunk. It's the same image, it's the same shape, it's just a different size, okay? So copying those notes down, and we're going to have a look at this in a little bit more detail. So, bit of a non-example, okay? Is the pig a mathematical enlargement of the painting? So what we mean by that is, are these two things similar? So what you need to think about is the notes that we just took down, okay? So they need to be the exact same shape. They can be different sizes, okay? And what you might notice is that they're not similar, okay? The proportions are very different, okay? This pig here, it's got this belly that kind of goes a bit lower than this one. The tail's not, present on this picture, okay? And the facial features are just a little bit different. They're squished up, whereas this guy has a much longer neck compared to this weird no-neck pig. So they're not similar, okay? They need to be identical to be similar. If you can imagine, in Word or using a computer, if you just grabbed like the corner of the exact same picture, right? If I grabbed this corner and kind of moved it in or moved it out to make it bigger or smaller, that would be a similar image. It would be an enlargement or a shrinking. Because this is a completely different image, they are not similar. There we go. So, the two sort of key words that we're going to be using throughout this particular topic is congruence and similarity. Again, that pencil's up the top right-hand corner, so I would like you guys to copy these notes down. Two shapes are congruent, okay, if they are the same shape and same size. So corresponding lengths and angles are equal, okay? So copying that down. If two shapes are congruent, they are the same shape and the same size. So that's a little bit different. It's one step on top of what we were talking about with similarity, okay? When we were talking about similarity, we were only talking about the shape. The size didn't matter, okay? They could be different sizes and they were still similar. So congruence is one additional requirement on top of similarity. So in an enlarged shape, the corresponding angles are the same, but the lengths are different. So these objects and its image are similar. And this is what we have down here. So these two shapes are similar, okay? So this is exactly what we were talking about before, about just, making shape A bigger. So what we can see is we can compare each side length. So we have this length over here is of length 1, right? 1 square, whereas this one has been enlarged to be 2. And that same enlargement factor has happened to every single side of this shape. Okay, if we play the same game, this shape was 1 square and now it is 2 squares. So it is exactly the same shape, every single side, right? Let's check this one as well. This one as well. 1, 2, 3. Well, this is 1, 2, 3, 4, 5, 6. Enlarged, they're similar, but now their size is no longer the same. So they are not congruent. Okay, and we're going to move on to those as well. So copying down those notes. Thanks, guys. Pause. Okay, so similar triangles, guys. Triangles are going to be our shape of choice when we are looking at similar shapes. We need a little bit of notation or some mathematical language. We have a symbol. So the symbol for is similar to, it's just a little squiggly line, and that squiggly line is called a tilde. You can see it on your keyboard next to the letter 1. So just draw it like that is how I tend to draw it. We can see, guys, we have a pen mark, so we need to be taking these notes down. When two shapes are similar, okay, their corresponding angles will be the same, even though their side lengths could be different. So their angles are what tell us that the two shapes are similar. So what we have, guys, is we have a really quick example here. And it is, well, let's have a look. We have triangle ABC. So this one here is triangle ABC. Okay, it is a triangle and it is defined by the points A, B, and C. Awesome. And it is similar to, okay, that's what that symbol says. That's what we wrote just above here. It's similar to triangle, okay, triangle symbol, defined by the points D, E, and F, which is, of course, this triangle over here, because it is defined by the 3 points, point D, point E, and point F. So they're similar. Let's have a real quick look at why they are similar. So we need to compare their corresponding angles. So the corresponding angles simply mean they're matching angles, okay? So if you imagine that triangle A, B, and C was a picture, we grabbed by the corner and stretched it out. We made it bigger, okay? We enlarged it. Well then, point A matches to point D, okay? And when we enlarge something, we don't actually change the angles in there. So this angle in here, this angle here at point A, okay? Well, that is actually the same size as the angle here at D. And we can see that represented in our picture by only having the one line, okay? Can we see that one line there? It's a little bit like when we draw rectangles, right? If we pretend this is a perfect rectangle, and we use those little geometric markers, those lines there to say, well, this side is the same length as this side, well, and then this side we use 2 to demonstrate that those two horizontal lines are the same length, okay? Same idea, just with angles. So the one line means that that is the same angle as this line, and then the 2 lines, okay, we can see that's 2, is the same here. So B matches to E, and they are the same size angles. And finally, C has 3, well, F has 3 as well. So they are the same size angle, they are corresponding, and so because all 3, A, B, and C, all those angles match to D, E, and F respectively, these two triangles are similar. Even though they're different sizes, okay, they're the same shape, the angles are the same, they are similar. That is how we're going to look at it. Okay, so what we have here, guys, is we have 2 similar triangles. Okay, again, even without reading this stuff, I can see that they are similar. I can see that they're similar because we have the geometric markers on our angles, they are corresponding, okay? So if I were to write a little statement here, I would write that triangle ABC is similar to triangle D, E, and F. I don't need to know anything about the side lengths, the angles are the same. That is what similarity is all about. But let's have a look at what this example is talking about. The scale factor of triangle ABC to triangle DEF is 2. So this means that the second triangle is 2 times as big. The ratio of corresponding sides is 2. So what's happened is triangle ABC has been enlarged by a factor of 2. So every single side length of triangle ABC has been multiplied by the same number, been multiplied by the number 2 to enlarge it. Okay, and we can see that. We had 8 times 2, 16. So those are corresponding side lengths. Okay, and then we had 6 times 2, well, that gives us 12. And then 9 times 2 is 18. So all 3 of those sides have been enlarged by the same factor, which is 2. So by using that constant factor, it ensures that our enlargement does produce a similar triangle, where all of our angles are equal to what they were when they started. Okay, so what we're going to look at here is, again, another way that we can tell
if two shapes are similar, okay? So as we've said before, similar shapes, they can be different sizes, okay? It could be an enlargement or a shrinkage of a particular shape. So the lengths of the corresponding sides are not necessarily the same, but they are proportional, okay? So we need to be a little bit careful about what that word means, and we're going to unpack that over the next few slides. So this is another way that we can tell if shapes are similar. So what this means is that if the shapes are similar, the ratios of the corresponding sides are all the same. So I understand we're using some big words, but bear with me, okay? What that means is that if two shapes are similar, so if two shapes are similar, okay, then we have this nice little rule. Okay, now what that does, let's unpack that a little bit. Okay, so we're using A, B, and C, as well as D, E, and F to define these two triangles. So what we mean when we say AB is the line AB, or the length of AB, divided by the length of DE. Whoa, okay, that is going to give us that scale factor. Okay, it's going to tell us how much it has been enlarged or shrunk, and that amount should be the same as BC. Okay, so the bottom side, that matching side, and EF divided by EF, so that matching side. So all three sides should have been changed by the same amount. Let's have a look at an example, and it should make a little bit more sense. So what we have here is we're trying to calculate this scale factor, okay? Because that is that proportion. That is the ratio that is being mentioned on the previous slide, okay? So what we have down here is we have triangle L, M, and N, and we are told in the question, right? So our question asks us to calculate the scale factor of the following similar figures. So we know that these two triangles are similar. So we know that LMN is similar to Q, R, and S. And what we're going to do is we're going to compare all three sides and see if we get the same ratio, if we get the same scale factor. So if this is our first side, okay, LM, well, LM is 12 units long. So what we do is we're going to compare all three sides. So hopefully you guys would agree with me, okay, that this L and M side corresponds to Q and R, okay? So what we mean by corresponds, they're matching. They are the equivalent sides for those two shapes. If triangle L, M, and N was shrunk down, okay, well, this top side matches this top side. Or put more eloquently, L and M corresponds to Q and R. That would be how we would describe that mathematically. Okay, and what we're going to do is we're going to write that as QR over LM. So that's that little equation that we wrote before. And what we found was when we put those numbers in, so the length from Q to R and the length from L to M was 9 and 12 respectively, and when we simplify that fraction, we got 3 on 4. So what that means is that if we multiply, okay, if we multiply LM by 3 on 4, we get the length QR. So it tells us how much or how our first shape was changed. Okay? It's the scale factor. And because it's less than 1, it means it was smaller, right? If you multiply a number by 3 on 4, you will get a smaller number. And that's what's happened. Our shape has been shrunk by multiplying by 3 on 4. And what we need to do is we need to make sure that all three sides give us that same proportion, that same ratio, that same scale factor. Because it is a similar pair of figures, those two figures are similar, we should multiply all three sides of our triangle by the same scale factor. Okay, and let's double check. So what we're going to do, we're going to compare two more corresponding sides. So we have RS, okay, this bottom left one. Yep, well that definitely corresponds to MN. Okay, we would agree that they are the same side. And we need to write, well, RS, that length was 6, divided by the distance between M and N, which was 8. We simplify that, and we got 3 on 4. Fantastic. Same scale factor, good. We're still on the right track for similar figures. And then the last one, which was that short side there, so QS divided by LN. Well, QS divided by LN gives us 3 on 4. Good. So the same scale factor has been used for all three sides. We have verified that. Good, so this is what we do, guys. I'll give you a chance to have a go at this one. Come back when you've had a go. Okay, guys, so what you're going to do is we're going to calculate the scale factor. So there's a couple of ways that we can do it, but what you should be asking yourself is, what number have I multiplied every single side of this shape to produce the similar figure of shape 2? Okay, and you might be able to do this by inspection. You might be able to look at this shape and realize, well, this side over here, ON, corresponds to this side over here, VU. And what number might I have multiplied ON to get VU? And did I multiply that number every single side? Okay? Well, you might be able to identify that. If we were to follow the rules previously, we would follow it a little bit like this. So what is the distance VU? And we're going to divide that by the corresponding shape, the corresponding side in our other shape. So VU, well, that is 6, and that corresponds to ON, which is 2, and we get 3. Okay, so if we multiply ON by 3, we would get our new size. This is the scale factor, okay? And what we could do is we could double check, righto, well, if I have LO is 5, multiply that by 3, well, yes, I would get 15. Okay, so that's one way of checking. If we go ahead, we should tick off all the sides. It's not too much work. So now what I'm going to do is I'm just going to go, let's go clockwise. So let's go MN first. So MN corresponds to TU. So we're going to go TU divided by MN. Okay, well, TU is 15 divided by MN, which was 5. Good. Same scale factor there. Let's double check the other ones. So we have ST divided by LM. ST was 6. LM was 2. Good. Well, that's also 3. The last one, SV on LO is equal to 15 on 5. And we got 3. So scale factor of 3, they are all the same. Scale factor is 3. So how we interpret that 3, as we said, it is the number that we multiply by our original shape to get our second shape, okay? Does the order matter? Okay? Yes, the order is very important. When you write a scale factor, if the scale factor of shape 1, okay, to shape 2 is 4, well, that means that the second shape is 4 times as big. And we saw that in that previous example, okay? The scale factor was 3, so that means that the second shape was 3 times as big as our first shape. And we can see that again here. What we would do if we were given, okay, oh, let's try that again. If we were given, okay, rhombus A, B, and C, parallelogram, excuse me, okay, we would have to scale it by a factor of 4. So we would multiply every single side by 4 times by 4, times by 4, times by 4, times by 4 to produce parallelogram W, X, Y, Z. Okay? So the order is very important. The scale factor is a big number, so it is enlarging. When we go the other way, so say we started with W, X, Y, Z, and we were to produce parallelogram A, B, C, D, well, the scale factor would be 1 on 4, okay? Because we would be, dividing by 4, or a better way to make sense of it would be to times by 1 on 4, okay? So that is the scale factor of going that way. It is the fraction inverse, okay? If you can imagine that 4 is the same as 4 on 1 as a fraction, well, then the inverse, we swap the denominator and numerator, is 1 on 4. So it is very important to understand which way we're going when we talk about constructing similar shapes. Similar shapes, remember, just an enlargement or shrinking of a particular shape. Okay, so a really quick redo here, guys. You can pause the video and we'll have a crack at this question in a minute. We'll see you soon. And welcome back. So what we're going to do, guys, run through this problem very, very quickly. It's not too bad. What we're doing is we are comparing corresponding side lengths, so matching side lengths. So I would argue, and hopefully you guys agree, that this side up here on the top, E to F, corresponds or matches to JK. So if we enlarged trapezoid EFGH, then side EF matches to JK in the new trapezoid JKLM. So they are corresponding, they are matching. And what we would do is, again, we would just, hang on, that's not a J, there we go. JK divided by EF is equal to 10 divided by 5, which is equal to 2. So that is how you follow the rules, and that is how we, just blindly think about it. But of course, what you guys can ask yourself is, what number do I have to multiply by this length to produce this length here, okay? And hopefully we could see, well, 2 times 5 is 10, so my scale factor is going to be 2. And then a really quick check, well, 2 times 7 is definitely 14. 2 times 8 is definitely 16. So my scale factor is 2. Okay, this one here, so we're going from STU to triangle PQR. So what number have we multiplied, okay, the side lengths of STU, triangle STU, to create triangle PQR? Now this one, guys, you might not be able to rely on your number facts as well. It's not a nice whole number, so you might like to think about this by using the rule, but it is just as straightforward, okay? So what I'm going to do is I'm just going to pick a side. We could do all 3 sides, but we already know the scale factor has been used. We know that these shapes are similar, okay? That's been heavily implied. So what we could do is just write something like this: PQ divided by ST is equal to, well, what are those values? Well, the length PQ, so the hypotenuse here, this long one, was 10, and then our hypotenuse of our first triangle was 15. We can whack that in our calculator. Let me just, I know how to do that. A bit awkward, I have to think about that, but 2 on 3. Okay, if you're a little bit worried about the order, okay, so the new length goes on the old, well, it's Queensland, it's old lengths, state of origin on my mind. New divided by old, okay? So we start with triangle STU, okay? And then we change it into PQR. So new divided by old. So that's why we had PQ first and then ST. Okay, another example here, guys. Give it a pause and I'll see you in a minute. Rightio, so what we're going to do, we're going to pick a side. I'm going to go, let's go A, B and D, E. Now, first things first, if we are starting A, B, C to D, E, F, so A, B, C is the old one, so A, B is old and it goes on the bottom, D, E is new, so it goes on the top, and let's substitute those values in. So D, E was 27, A, B was 9, I know that one, we'll get one right, is 3. So the scale factor is 3. And we can double check, yes, okay, so 3 times 9 is 27, 3 times 9 is still 27, and then we need to check that one. Well, 3 times 7 is 21, good. So scale factor is 3. That's it, guys. Thanks for tuning in, and I'll see you next time.